Hi everyone, my name is Behlul Fatami Zahra and I'm a doctoral student in the National Institute of Statistics and Applied Economy. I work under the supervision of Professor Qadrani Abdeslam. I am delighted to present our research work on bi-level optimization at the 11th Conference on Optimization and Applications. This presentation is structured into 4 interconnected parts. We begin with the first section, which introduces the motivation and problem under consideration. The second section focuses on a single level reformulation and convex decomposition. And in the third section, we develop a duality-based approach and optimality condition for problem noted by P lambda epsilon, and finally, under some as hypothesis, we derive necessary optimality condition for our original problem noted by P. Bi-level optimization problem is a special class of a hierarchical problem in which two decision makers interact sequentially, a leader and follower. The leader makes a decision first and then the follower responds by solving an optimization problem that depends on the leader's choice. Such models arise in various applications, for example, energy market, transportation, planning, production management, and also network design. In our work, we are interested by a special class of bi-level optimization problem, namely the semi-vectorial bi-level optimization problem, when the lower level problem is multi-objective and the upper level problem is scalar. In what follows, we address the optimistic semi-vectorial bi-level optimization given by minimizing a function var phi such that the variable v is a weakly efficient solution for the lower level problem, which means that there does not exist any other solution improve all objectives function simultaneously. The set K is the set of feasible points defined by the following inequality. We assume that all functions are convex and the sets U and V are compact and convex. We recall that in the optimistic approach, the two levels cooperate on the sense that the follower chooses response that is most favorable to the leader, which means that the leader chooses its decision variable u, and the follower then minimizes the parametric problem, minimizing sigma over the feasible set, and then providing the solution that is most favorable to the leader. This type of problem is generally non-convex, even if the objective functions are convex. Also, the multi-objective structure generates a multiple follower solution, which make the leader's decision more complex. First, to address the multi-objective nature of the lower-level problem, we proposed a weighted sum approach. In this approach, the multiple objectives are combined into a single scalar objective by assigning a weight to each objective. The bi-level problem can be formulated as follows. Minimizing the function var phi such that the variable v is a solution of the lower level problem after scalarization. A key advantage of our reformulation is that the parameter lambda is not treated as a variable, which eliminates the need of joint convexity assumption. As a first result, linking the original problem with the problem obtained after scalarization, the lower level problem, we have the following proposition. Let U, V be a locally or globally optimal solution to the problem P. Then there exists a vector lambda such that V is a solution of the lower level problem after scalarization, and U, V is a optimal solution for the problem P lambda. To extend our feasible domain, we introduce a regularization through a positive parameter epsilon, and as a stability result, we have the following theorem. If U, K, and Vk is a sequence of solutions to the scalarized regulated problem P lambda epsilon k, then any accumulation points of UK, Vk is a solution of the problem P lambda. Since the regularized problem is non-convex, classical duality theory cannot be applied directly. To overcome the limitation, we first reformulate the regularized problem as a minimization problem with difference of convex constraint. We then introduce a suitable decomposition of the regularized problem. This reformulation enables us to explicitly derive the functional Lagrange dual of each sub-problem. As previously mentioned, the regulated problem is non-convex, therefore we will use the decomposition introduced in the previous section since the resultant sub-problems are convex. We begin by defining the extended functional Lagrange duality associated to our problem P lambda epsilon. We define the weak duality by there exists a vector U star such that the following inequality is satisfied. The same, we define the strong extended functional Lagrange duality. To ensure a strong duality, we introduce the following Slater type constraint qualification, which guarantees that at least one strictly feasible point exists. Feasible point exists. Theorem 3 derives necessary optimality condition for our problem P lambda epsilon. The notation var phi star and sigma lambda star denote the functional Lagrange dual of the functions phi, var phi, and sigma lambda respectively. The theorem 4 derives sufficient optimality condition for the regulated scalarized problem P lambda epsilon. Finally, and by using the previous results, we can derive necessary optimality condition for our original problem under some hypotheses. The Theorem 5 is a combined result of Theorem 3 and Theorem 1, which assumes that every accumulation point of a solution of P lambda epsilon k is a solution of the original problem. As conclusion, steps of our method are illustrated here. This concludes my presentation. Thank you for your attention, and I welcome any question or comments.